Hi, in this video we will do an example which involves some Gram-Schmidt process at some point. The question asks for the orthogonal decomposition of vector v with respect to the subspace spanned by these two vectors. Remember that what we do in that case, v is sum of projection of v over w plus perp v over w. But projection of v over w needs to compute this. We need an orthogonal basis for w. Okay, but what we have here, if let me call this one x1, this one x2. x1, x2 is just a regular basis for w. It's not orthogonal, just dot product. You notice that it's not orthogonal. What shall we do then? Then we'll use these ones, make v1, v2, which is an orthogonal basis. And here we need Gram-Schmidt process. And how does that work? Well, v1 is exactly x1, which is just, what is this? 1, negative 1, negative 1, 1. And v2 is x2, but you have to throw away part of x2, which is in the direction of v1. So we have 2, 1, 0, 1, yes, minus projection of this guy. So it has a scalar, then in direction of b1. Okay, dot of this and that is in the numerator, so this is 2 minus 1 plus 0 plus 1 over 1 squared plus 1 squared plus negative 1 squared plus negative 1 squared. All of them, this will be 4 in the denominator, 2 in the numerator, so this is 1 over 2. So v2 is 2 minus 1 over 2. Yes. 1 minus plus 1 over 2. 0 minus 1 over 2 times negative 1, which is plus 1 over 2. 1 minus 1 over 2. So v2 is 3 over 2, 3 over 2, 1 over 2, and 1 over 2. So we formed that orthogonal basis. Well, this is 1, negative 1, negative 1, 1, and 3 over 2, 3 over 2, 1 over 2, 1 over 2. Well, is this the only orthogonal basis we can make? Well, this is the one we got from the Gram-Schmidt, but if you multiply these vectors by any constant, you still get orthogonal basis. Let me leave it like that. And now that I have orthogonal matrix, orthogonal basis, I can find projection of the vector v on to subspace w, which is projection of v over v1 plus projection of v over v2. Here, v1 is 1, negative 1, negative 1, 1. And v2 is this? 3 over 2, 3 over 2, 1 over 2, 1 over 2. Each one has a scalar, so this one dot v. V is what? 1, 1, 1, 1. Okay, so we add all these guys. 1 minus 1 minus 1 plus 1 over 1 plus 1 plus 1 plus 1. This guy here, this will be 3 over 2, 3 over 2, 1 over 2 plus 1 over 2. And square of all these guys will have 4 in the denominator, 9 plus 9 plus 1 plus 1. Okay. Well, the good thing is that this guy is 0, so we will have first part is gone. The second part here, this is what? This is 20. In the denominator, we have 20 over 4, which is 5. Okay, nice. And in the numerator, we have what? Half 3311, that is 8 over 2, which is 4. So 4 over 5 times the different components that we have. So over there it will be 6 over 5. I'm multiplying and simplifying at the same time. 6 over 5, 2 over 5, and 2 over 5. So projection of V over W is 6 over 5, 6 over 5, 2 over 5, and 2 over 5. How about perp V over W? This is going to be just V minus projection of V over W. And that is 1, 1, 1, 1 minus the projection of V over W we just found. 6 over 5, 6 over 5, 2 over 5, and 2 over 5. This will give us negative 1 over 5, negative 1 over 5, 3 over 5, and 3 over 5. So the decomposition of V, orthogonal decomposition of V with respect to W is going to be 6 over 5, 6 over 5, 2 over 5, 2 over 5, plus negative 1 over 5, negative 1 over 5, 3 over 5, and 3 over 5. And that's how we find. And remember, what was new was that we started with just a regular basis, but we found an orthogonal basis using Gram-Schmidt from that, and then found the orthogonal decomposition of that vector.